Okay, good. I think just for the sake of timing, maybe let's get it started. So today we have Yuxin Chen from Berkeley. He is a PhD student in Professor Tomizuka's group, and I actually met with him when I visited Berkeley last December. So we have some fun chat there. And I think if based on what I remember, I think Yuxin has been largely working on RL whole body control for both locomotion and manipulation problems. And just from the title, I think you would talk a little bit more about the manipulation sides, but definitely incorporating, whole body coordination. Um, so with that, yeah, Yuxin, please take it over. And thanks for giving this seminar with us. Thank you.
Sure.
Yeah.
So first, thanks invite from Professor Zhao and also Zhigen. So today my title is Scaling Mobile Manipulation from Whole Body Coordination to Open World Semantics. A brief introduction to myself, in addition to the intro by Professor Zhao. I'm Yuxin Chen, and currently I'm a fourth-year PhD student at UC Berkeley Mechanical Engineering Department, and my advisor is Professor Masayoshi Tomizuka. And in the past, during my PhD study, I mostly focused on first is the whole body control of both the quadruped robot and also bipedal robot. And second part, I focus more on the preference alignment via the inverse reinforcement learning, via the fine-tuning diffusion policy or the fine-tuning VLM models. And recently, I focused more on embodied AI and also the open world deployment of different kind of mobile robots. And in the last year, I spent 6 months interning at the Ray Institute, which used to be the Boston Dynamics AI Institute. So today I'm going to briefly introduce the two projects I conduct during my internship at the Ray Institute. The first one, the title is Versatile Local Manipulations Through Flexible Interlimb Coordinations. The motivation is simple. We'd like to see whether the robots can interact with objects using not only arms, but also the leg. Because in the past, once we have the quadruped robots with arm equipped, we usually just manipulate with only the arm. We treat the lower body as a whole moving platform. For example, we have this, I think this is from Xiaolong Wang's group, and this is from Shuran Song's group. And sometimes people also have the using lag for manipulation. For example, these two are, I think, one from CMU and one from, I think both are from CMU. Yeah, so they just attach additional foldable arm into one of the leg and then treat the leg as the arm when the robot is standing up. And in that case, they also have some certain limitations. For example, they assume the prefix limb roles. For example, the arm are always used for manipulations and leg are always used for locomotion. But on the other side, like in this cases, we also have some task-specific design. So we have to manually add additional mechanical system structures to the robot to enable some predefined tasks. But in the real life, like we humans, we can perform really complex tasks by jointly using multiple limbs. So for example, we can use not only the hand, but also the arm and also the chest to have multi-contact points in like supporting a large pile of boxes, while also use the leg to support a door. Or on the other like side, for example, like we use both arms to one arm hold up the lid of the trash bin, and the other arm like throw in the bottles. Or in this case, we have like multiple fingers movements on the guitar, and also we have the feet touching the pedal on the ground. So in this case, can we actually realize this kind of complex limb-wise coordination on the quadruped robots? So this is our motivation. In that case, we can manipulate with both arm and leg while walking, and also say manipulate with arm and leg while standing, or do the multiple arm task. And also like this long horizon, they have multiple step. So we define a task like this. For example, we try to transport a yoga ball from one end to the other side of the room. And given assigned roles of limbs and their target trajectories, here we specify two actuators. One is the arm, which is labeled as green, and one is the leg, which is labeled as red. In that case, we try to jointly control both the arm and legs to solve this task. Say we use both arm and leg to lift up this yoga ball and then move the yoga ball to the other side of the room. The key challenging involves we have to precisely perform manipulations with both arm and the selected leg. And also, during this task, we have to maintain stable locomotion with the remaining three legs. And our aim is to first enable flexible coordination strategies and also have dynamic limb assignments. And also, we need to define a versatile task specifications so that the system can not solving this single task, but also a diverse set of tasks. And our method, we call it reinforcement learning for interlimb coordinations, or RADIC. It's a controllers running at 50 Hertz on robots. And the major feature is we involve a binary mask to specify which arm, like which limb we're going to use for the manipulations. Here we have 5 cases. For example, the arms, like the single arm mode, or a arm plus one of the leg. So we have 5 modes in total, and we treat this as additional input to the controllers. So here, for example, we try to use the front right leg with arm for the following manipulation task, and then we feed this mask into the controllers. Together with a leg target and arm target, we manually specify how we want to move the leg and how we want to move the arm. And then based on these two trajectories, we use the inverse kinematics to solve for the body target, which is the blue trajectories. We solve for all these 3 targets and then feed into the controller together with the robot state as well. And finally, the state will output the low-level actions, which is the joint space command for the 7-degree freedom's arm and also the 12-degree freedom's lower body. But here we have 2 modules, right? So because the upper body, basically the lifted arm, the lifted leg and arm, they serve as the manipulators, and we need to let these manipulators to perform really precise manipulations to interact with the surrounding objects. While the lower level robots, like the low level, which is the leg, the remaining leg, they have to remain contact with the ground and also do the locomotion and balancing. So these 2 modules has the objectives are not different. They're quite different. So it's really hard to train a end-to-end policy, for example, reinforcement learning policy, to handle both modules at the same time. Therefore, we split the controller into 2 parts. One is the model-based controller, which explicitly control the arm and the leg motion, the lifted leg motion, or say the manipulator motion. And the other half, we use a reinforcement learning controller to control the balancing leg motions. So in that case, we decompose these 2 modules so that each module can achieve the best performance on their own. And for the inference, how we define the desired arm motion and also the leg motions, we have 3 kind of interactions. One is the direct target, another is the contact points, the third is language instructions. So for the direct targets, we just use a 2 spatial mouse to manually control the desired trajectories of the arm and the leg. And the second contact point, it's more like a mix between the direct control and the VLM. So at the first, at the beginning of the task, we capture a image. So here we capture an image, and then we convert into a 3D point cloud, and then we provide an interactive interface for the user to specify the contact points you want the robot to interact with. And then once we have specified the contact points, the robots will linearly interpolate a trajectories from the current pose to the desired contact pose, and then do the following task. So we specify the pre-contact and post-contact. And the third one is fully automated. It's called language instructions. So we give, say, the GPT-4o model a language prompt, how we want the robot to complete this task. And then the GPT will, based on the given image, manually specify the segmentation with the segment anything, and then specify all the contact point candidates, and then choose the correct one from this candidate as the final target. Once we have the final target, it will just do the following task automatically. Okay. So how we train this low-level policy? We train this in the Isaac gym and then deploy in the real robots. So there's a huge sim-to-real gap in this case. How we gap it? We do two tricks. One is the motor calibrations. We try to find the physical properties of the motors, especially during the high torque regions, because during the high torque region, the motor response is not that linear. So we just do a lot of system ID to actually fit a curve and feed it into the simulator to correctly model the behavior of the motors. And then we also include the gate regulations to constraining the contact time pattern to stabilize locomotions. I have some example in the next slides. So here we try to show the robustness of the controllers. For example, at certain pose, we can lift up any leg, and then the robot can just remain stable for a long time. And in the meantime, it's really robust to the external disturbance. We can push, we can punch the robot, it can remain stable. So another thing we want to highlight here is the end-effector tracking. So here we only input desired trajectories of the end effector, which is the arm, and also one of the leg, to follow the two spatial square trajectories in a 3D space. And it can try to follow this trajectory pretty good while moving the robots using 3 legs. So here's a plot shows it's very stable. Like we just do 10 rounds. The robot just do 10 clockwise look motions, and it will not drifting. Here's a ablation study. Like without those tricks, you can see the tracking area is very large, and the robot just try to decay because the motor calibration is wrong. And the sim-to-real gap will just try to accumulate the tracking errors. And if we don't have the gate regulation, it can not simply support itself. So for the motor calibrations, as I mentioned previously, if the motor has super large loads, we will have a very large sim-to-real gap. So all these blue points, we just sample using system ID, and then we manually fit a curve, and then feed this into the hyperparameter setting of the IR training. And here's some quantitative results. And another thing we like most on this project is that it can enable the seamless gate transitions. So here you can see we have different patterns. We have either the 3-leg locomotion patterns or the 4-leg locomotion patterns. And then during this, the gate switching, we don't have to stop the robot. So, because usually people manually train different IO policies, say with the 3-leg policy, with the 4-leg policy, and they have a state machine to switch between these different policies. And then during a switch, they have to stop the robot and then switch to the other policy. But in this case, because we have a mask as an input to the policy, so they can dynamically change desired gate during locomotions. So you can see there's a seamless transition between the gates. There's no pausing required, there's no failing required. And here we show a demo without the gate regulations. This is purely emerged from the reinforcement learning. So if we don't have additional constraint to the reinforcement learning trainings, it will emerge some weird behaviors, which is not desired, because just try to jump with all 4 legs. And you can see it's just bouncing up and down, so the tracking error is very large. Right. So we validate the whole systems with 12 different tasks. We grouped it into 3 categories. The first category is called mobile interlimb coordinations, which means we have to, the robot have to do the manipulations with both arm and leg, and also keep walking. So here's 2 examples. You can try to move the yoga ball from one place to the other, or a shipping box. The shipping box is more challenging because it is rigid, the rigid body. So if we have a slightly offset on the contact point, it can't actually lift up the box. The box will just tilt it down. The second category, we call it manipulations with arm and leg while standing. In this case, the robot is not moving, but actually it has to do multi-contact manipulations to complete the task. For example, here we try to pump the tire, so we have to let one manufacturer to stabilize the pump and the other one to actually push the pump. Or the trash bin, we have to one contact to press the pedal to lift up to open the lid, and the other manufacturer to actually put the object inside the trash can. And the third category, we call it assist or accelerations. So in this case, single contact manipulation can also successfully do the task. But if we involve additional manufacturer, it can accelerate the whole task. So for example, in the shopping scenarios, if we only have one hand, we have to lift up the basket, and then once we're facing the shelf, we just put down the basket and then use the hand to pick object into the basket and then to lift it up. But in the real life, right, like we usually have one hand holding the basket while the other hand picking the object put into the basket. So it's more human-like and more realistic settings. So in other cases, for example, the storage bin, we can use one leg to drag the storage bin while the other arm to pick up object and then throw into the storage bin. So all these previous examples are demonstrated by the direct target, which is head operations. So here we choose 4 of the tasks to showcase the contact point planning, which is the second way of interactions. So in this case, we just take the image and then project into the 3D space as an interactive 3D point cloud, and then ask the user to specify the points in the 3D space to let the robot do the automatic task executions. So here's the example. It's kind of lagging, but basically via this interface, we can also do this kind of task quite successful. And we also tried do the fully autonomous version, which is the language instruction planning. We just used the ChatGPT 4.0 to do the fully auto execution on the yoga ball task and also the tool chat spec. So in this case, everything is automated. We just provide an initial image and a text prompt, and it can do this task. So here, try to use both arm and leg to close 2 drawers of the chest. Okay, so here's a gate pattern, a gate map to show the different role during long horizon task. So here, in this case, the arm in the early stage is served as the pure arm manipulations, and the leg serve as the pure leg manipulations. And after that, it also involves the interlimb coordinations. We have to keep the arm holding the lid while the hand to put the scuff into the box. In this case, the arm is keep holding the chair while we switch to different leg to push the bin consecutively. We do some baseline comparison because all these tasks we choose for this project involve multi-limb coordinations. So we like, as I mentioned previously, it's really hard to train the end-to-end reinforcement policy, because if we focus more on the stabilizability of the locomotions, then it will sacrifice the accuracy of the manipulations. It will simply can't reach the object as good as possible. And if we focus more on the manipulation success rates, then the robot may not actually move. It will just tend to stay there, or it will, whenever it moves, it will just fall down. And an MPC is the embedded controller by Boston Dynamics, and they don't have the feature enabling additional lag lifting up. So their policy can only support 4 leg locomotions. And here's some failure cases. In most cases, it either failed by the slamming accuracy. There's some misalignments between the 3D mesh of the perceptions, or sometimes we have the controller failures, especially when we have the cases where the robot has a very large interaction force with this external object. And in that case, especially when the robot is standing with 3 legs, it's already very not stable. And then if we have a large external force, it will tend to lose balance. And the third case is more tricky cases. For example, the yoga ball itself is plastic and pneumatic. So it can just try to bounce away if we just not grab the yoga ball with correct locations. Okay, so this project focused more on the low-level controllers of the robot, which we call it whole body control. So how about high-level reasoning? How about say we put the robot into a open vocabulary settings, how the robot gonna plan a task as a high-level planner.
So sorry, Yuxin, can we stop for a second? There's some question. So yeah, I think this is a very, very cool work. I'm just curious, like when you say there's a dynamic limb assignment and some of this contact information planning, these are done not within the low-level RL controller, right? This is done by the higher levels. Is that right? Can you talk a little bit where? Yeah.
So yeah. So basically, the RL controllers can take either 3 legs or 4 legs, and the objective is just try to follow the desired body target. So we specify this blue trajectory with desired body targets. And the RL policy is just try to move the robot body to follow to track this body target, and it can either track with 3 legs or 4 legs. And the manipulation side, we use model-based controller, so we just specify the desired end effector pose, and then we manually optimize a trajectory from the current pose to the end effector pose. To design end effector pose, and then use a model-based tracker to track these trajectories. Yeah.
Okay, so there's some like a high-level, contact sequence design, or the limb assignment. This is done by the higher level, maybe some rule-based or other approach.
Yeah, that's why. So how we specify this high-level inputs? We have three kind of inputs. Either the TED operations, we manually specify the location of this end effector and the lift lag, or the contact points, which is we specify the end points and then just do the interpolation between, and then follow that trajectories. Or this is more like the end-to-end high-level planning, but in that case we just use the GPT to visualize to specify this contact point. So the trajectory itself is still just by the interpolation.
Okay. Okay, I see. And then if you go to the next slide, you have this upper body model-based controller, and then the lower body is RL, right?
Yeah.
And I wonder if there's any interplay or interaction between these two controllers, or they are sort of controlled, they do the upper body, the other one the lower body.
Yeah. So in this case, the model-based controller is pretty much assume it's just doing a floating base manipulations. So based on the current body targets by the proprioceptive states, and then do the forward kinematics to try to reach the desired target. In the lower body, the RL controllers, during the training, we just do some domain randomization to account for the external forces exerted to the upper body, to the end factor, and also the lifted leg. So in that case, the lower body just try to robustly reject any potential disturbance. But if the force is too large, then it can still lose balance, as I mentioned in the failure cases. So if, for example, we try to use this leg to push down, like to step on a pedal, and if it's push it too hard, and then the forces like exceed the limits of the RO control robustness region, then it will just fail.
Mhm, mhm. So, and you mentioned that this kind of combination is is better than just do a whole body RL controller for
Yeah,
both.
yeah, because the IO controller, like it's really hard to tweak the reward, because if we focus more on the say the manipulation reward, it will just try to reach to the like let the end effector to reach to the desired location as good as possible. In that case, the robot may lose balance. It
Hmm.
may not like provide smooth gait. And then
Yeah.
if we just emphasize too much on the stabilizations, then robot just tend to stand there. And
Hmm.
the offset between the manipulation can be larger than 10 centimeters or 20 centimeters. In that case, it's not possible to do any like precise manipulation task.
Hmm. Yeah. Yeah, we have some other observations about this. I think, kind of they couple the upper body, lower body controller. Like
Yep.
the when we do local manipulation, usually the local motion actually cause a lot of vibrations to the upper
Yeah.
body. And then if you want to stabilize the upper body, for some stable manipulation tasks, it's actually very challenging. So we kind of use leverage model-based controller to kind of compensate some of the vibration errors for the upper body.
Yeah.
So that's a little bit different architecture. It's kind of RL for whole body, but the upper body is further informed by the model-based controller, so which for stable manipulation problems. So again, some
Yeah.
work reason, I feel this some yeah. I think if you want to do both good locomotion and stable manipulation, you really need to inject some model-based information into this.
Yeah. So in this case, most of the task when we so only the first category we have the like bimanual manipulation while walking. In that case, or once we hold it like during the picking up motion, the robot just standing there. So there's no vibration from the locomotion side. So once we
Mhm.
pick it up, we start moving. So
Yeah.
in that case, we try to avoid this kind of more complex problems. And in other cases, like during this kind of motion, you can see during the manipulation, we also try to just let the robot stand there. But uh, once we have a fixed contact with the object, then we can do the start. We start the locomotion.
Yeah.
Yeah.
Cool. Nice.
I have a question.
Sure.
Could you go back to the system diagram
Okay.
page? Yeah, this one. So about this like fusing model-based controller and RL controller, like are you sorry, I didn't get it, but are you fusing the both controller for the whole body control or just the manipulation?
Sure.
Process?
So in this case, like robots, we have each leg we have three degree freedoms. So
Yeah.
the lower body we have 12, right?
Mm,
And the upper body, the arm, we have 7. So in
okay.
total, it's 19 degree freedoms. So in this case, once we have with a leg lifted up, it's no longer a balancing leg. So it's no longer for the locomotion, it's more for the manipulations. So in this case, we just output the 7 plus 3, which is 10 dimension from the model-based controllers, and the remaining 9 dimension from the IL policy. So here you can see we have a mask. So this mask is the show one is the arm, one is the leg, right? So the model-based controller just outputs all the dimension, but we only take the masked version. So we only take the arm and the front right leg. So those
Mhm.
commands to feed to the robots, and the remaining comes from the RL controllers.
Okay, okay.
Yeah.
So when you train the policy, right,
Yeah.
you don't really inject any NPC. feedback to the RL
Yes.
control. So you just like I guess for the RL control, you just train the 19 DOF for the assurance, I guess, and
Oh
then
no.
when
So the RL controller training. Let me see. I have a figure here. Yeah. So during the RL controllers, we keep this arm here, but the arm just do some random stuff, and
okay,
then
okay,
the RL controller just try to stabilize the robot, and then try to track a predefined body trajectories with either 3 legs or the 4 legs. And the upper body, like this arm, we just give some random motion to simulate the actual deployment scenarios. For example, the external forces, the change of center of mass, like in that case. Yeah.
okay.
So,
So
so
I guess
maybe
you have you have
let me just ask one more thing. So in this case, actually, the upper body motion is kind of like a perturbation to the
Yeah.
lower
Yeah.
limb, and
Yeah.
then the lower RL controller is robust enough to
Yeah.
be able to handle all different kind of, upper body
Exactly.
motion, right?
Exactly.
So that's
Yes.
okay. That's okay. Cool. That's actually we do this in the other way to do the upper body. So, but it's interesting observation. Yeah, yeah. Okay, good,
Yeah.
good. Yeah, Junso, go ahead if you have more questions.
okay. So I guess your RL controller takes the mask information so that you can switch between like 4 leg
Yeah.
locomotion and the
Yeah.
3 leg locomotion plus
Yeah.
1 leg in the air, right?
Yes.
Okay.
So yeah, so the mask is also additional is also a observation feed to the our
Yeah.
controllers. So it also feed at 50 hertz. So that's why we can just dynamically switch during the executions, and it can suddenly
Okay.
just switch the gate.
Okay. So I also have questions about model-based control. So
Mhm.
what kind of model-based control are you using? Like, are you
Oh,
using the one from the spot or like the
no,
uh
we actually implement our own model-based controller. That's very simple. So basically, we just do a trajectory planning, right? So we specify the manufacturer desired contact point and the current contact point. We just do a interpolation, how the robot gonna move from this point to this point. You solve the inverse kinematics, and then just try to have the PD control for each joint to follow this
okay.
desired trajectory. Yeah.
Okay. Cool.
Yep.
Thank you.
So I actually have just maybe a minor question. I know this Boston Dynamics Spot robot. There other groups has been working on the RL for the quadruped, and I assume they have very good robust simulator, even taking into account the torque level or the actuator level dynamics. But I think you show some components even for your work, you need to further fine tune or do some maybe identification
Yeah.
for
Yeah.
the
Yeah.
motor level dynamics. Is this because you are doing this particularly for your task, like this local manipulation task? So you need to do
Uh,
this actual
so
work.
so basically, so this part is not done by me, but this the system ID is very important. So we try that. Like if we don't explicitly do the system ID, the symmetry row gap is still super large, especially when the robots try to do 3 leg bouncing. Because
Mhm.
if we have 3 leg bouncing, each leg having like more, like each motor have more load than the normal cases. And in that case, there's a nonlinearity exists, and then the IO policy gonna fail. So I think the people in Ray Institute, they do the system ID to all the robot they have. The Spot, the G1, the H1, also the E Atlas. They do all those system ID to find the accurate motor parameters to guarantee a smaller symmetry gap transfer.
Okay. Do they open source this or probably not?
That's not open source, but I
Okay.
think the Beyond Mimic by Cha Yuan,
Yeah.
he that work is partially done during his internship at the Boston Dynamics. So I
Mhm.
think I heard that like he actually used the system ID results from the Boston Dynamics. So the Beyond Mimic is really robust. So I think now, like if you wanna uh, deploy some RL policy on the G1, you can directly adopt their PD gains from the biomimic. Yeah, I tried that. It's very robust.
Cool. All right. I think Feiyang is doing that.
Yeah.
Yeah.
Okay.
Thanks.
So yeah. Then let me continue. So this work we focus more on the whole body control. It's more like low level. We don't really care about the high level reasoning. Like we partially show, okay, we can sort of use the VLM, but that's just a small portion of all the tasks. So mostly we just try to show the robustness of this whole body controllers. In the second project, we focus more on the higher level planning. So this recently submitted to the RA letter, and we're doing a rebuttal right now. The open world, the title is Open World Mobile Manipulations via Structured Affordance Groundings. So this work focuses more on the representation side, so the intermediate level between the text inputs and the low-level control. So nowadays, like when people talk about open world robotic control, we just usually mean the VLA models, the big foundation models, like almost all the startup companies nowadays, they have their own VLA models, but they have certain limitations. So first, they require a large data set, and that data set also highly labeled. It's very expensive to get those high quality data nowadays. And then the second limitation is also very severe, which is the poor out of distribution generalizations. So even if we train the foundation model from a very large data set, we still have to make sure the deployment scenarios is kind of in distribution. It's not really good to handle out of distribution cases. And like similar thing, like if we try to do the cross embodiment deployment, the performance is dropped severely. And so there's another way to do this kind of task, which is early style. For example, the say can or the proc prompt. So they assume a predefined skill set, and then they just use the VLM model to do some semantic level high level plannings, and then use that semantic level planning to execute the low level skills. But in that case, we need a hard coded motion primitives, and also the performance is very limited to the predefined robot skills. So in this work, we try to find whether there's a spatial grounded affordance-based task representations serve as an intermediate level, so that it can achieve versatility, which means we can use these representations to represent many tasks, many different style of tasks. And modularity means this can serve as a plugin strategy. We can adopt these task representations to many other applications. And abstraction means we want this task representation to be as low level as possible, as simple as possible. And grounding means we want to inject the spatial information, the physical information, or the spatial, the semantic information to this task representations. So here's one example. We try to tell the robot to step on the platform. And then here we define 8 different affordance. So they're very generalized affordance definition. For example, the grasp, the place, the function, which is very similar in the manipulation scenarios, and the direct contact, indirect contact, and the void, walk to, step on. So we try to use all these 8 affordance to represent most of the skills. So all the long horizon tasks can be decomposed into these 8 unit affordance. Say step on the platform, we like to see the platform is highlighted, and then the robot can actually step on the platform. And then after it step on the platform, we try to grasp the duster and use the duster to sweep this snack bag to this box. So it can actually try to grasp this the brush, and then use the bristle to sweep this snack bag to the box. So in this case, like we had a point cloud, and then each object has each affordance has corresponding highlighted point clouds, and then robots just do the task afterwards on top of that. So here's execution videos, try to just sweep the snapback into the box. So how we achieve this? We define this method, we call it SAGA, which is structured affordance grounding for actions. So for each this affordance, we have a latent embedding. And then in addition, we have additional embedding for the motion, which is the motion encoder. Because for example, when you try to grasp a object, you can either reach from forward or from right to left or from left to right. So in that case, the motion itself, the grasping should be the same. We can just specify additional directional guidance to guide the robot to move from a desired location. So here, for example, if our text prompt is pick up the eggplant and put it into the open drawer, then we know that the eggplant corresponding to the grasp and the open drawer corresponding to the place. So we encode this eggplant as latent embedding for the grasp and the open drawer as a latent embedding for the place. So given an image, this is the current observation from the in-hand camera. We can extract the visual features by dyno, and then for the visual, we can try to find a cosine similarity between the visual features and this latent embeddings, so that for the grasp, we can calculate a attention map or a heat map to highlight which object we want to interact on this current image frame for grasp. Similarly, for the place, we can see the corresponding pixel of the open drawer is highlighted. For step hum, because there's no feature we want to interact with, like with step hum affordance. So step hum is basically 0. So we calculate the affordance heat map for each kind of affordance, and then we combine this with the raw point cloud, which is the raw 3D point cloud. So we can lift this 2D heat map to the 3D point cloud map, so that the resulting point cloud not only includes spatial information about the object shape, about the object location, but also the semantic and affordance meaning from the text, from the user input. So once we have this heat map informed 3D point cloud, we can then feed into a policy. So we call it SAGA policy. So this policy is essentially just a diffusion head. So it inputs the motion embedding, which is the directional instructions, and also the initial observation, including the semantic meaning from the previous part, and also the current observations, the current 3D point cloud, and also proprioception, which shows the robot current state. And we get all this information feed into the diffusion head, and then the diffusion head directly outputs a action chunk to do the task execution. So this is the basic idea. And another thing is how we specify this affordance dictionary, right? So the previous example I provide is through language. So once we have a language, we can directly use the ChatGPT to decompose the language into a dictionary with keyword. So we can provide this list of affordance, and then ask ChatGPT to decompose this whole sentence into this dictionary. So grasp corresponding to an eggplant, place corresponding to a drawer. Or we can do some interactive way. Just give an image. We prompt the user for each affordance. So now we ask user to click which pixel we want to choose for grasp. And then the user can just pick a random pixel on this image, and then it will find the corresponding visual feature of this pixel, and then find all the similar pixels with sharing the same visual feature or close visual features. And then it can specify, okay, if I just click a single pixel on this eggplant, then it will highlight the whole eggplant. It's the standard feature by the Dyno V2 nowadays. Or we can do a few shot learning, which basically saying we have a policy, we just freeze it, and then we provide some few shot human demonstrations. We just do the tail operation to collect all these demos, and then let the robot itself to specify like which embedding corresponding to the task. So I'll explain it later in an example. So how we train the diffusion policy? We collect 2,400 samples. Okay. We collect 2,400. I think it's around 2,410 rollouts. So in this rollout, you can see this is the in-hand camera. So we just pick up something, play something to something else, or we just step on something. And 70%, like most of them are still about grasping, about placing, about locomotion. But in this case, for example, the demo, we try to pick up a Santa Claus, right? Or a brush. But in the deployment time, we can directly generalize this policy to some unseen objects, as long as they have the corresponding visual feature highlighted by the text prompt. So here's an example of the zero-shot execution. For example, here, the text prompt is walk to the coffee table. So it will try to highlight the coffee table corresponding point cloud in the three point cloud map. And then it will try to approach this coffee table. And then it will capture another image. Say, push the basket forward. So the forward is the motion embedding. It will try to highlight this basket and then try to push the basket forward. And the third task is more long horizon, more complex. I try to just grasp the brush, and then use the bristle to sweep the snack back to the basket. In this case, you can see the grasp corresponding to this handle. The bristle is the function, how we're going to use a certain part of this object. So the bristle is highlighted as purple, and the green is the indirect contact, which means we try to use this bristle to have contact with this green bunch of point clouds, which, like for the policy part, it don't really need to know whether it's say the snack bag, or it's a puppet or something else. For the policy level, it's just a bunch of highlighted point clouds. So in that case, it's internally support generalizations, as long as we provide corresponding a correct heat map. Then the policy can just do the following task with some pre-trained policy on other objects. So yeah, this is the rollouts. Okay. So in this case, it's another one. Try to step on the stairs, grasp the doll, the bear, and place it into the basket. And then lift up the basket up. So you can see it's highlighted the handle of the basket. And this one's more complex actually, because this is mobile manipulations. So once we specify, okay, you try to grab this eggplant on the ground, it has to first try to move forward to the eggplant, and then place it into the open drawer.
So quick question, does the robot or the policy know the object semantics? You mentioned it's just a set of point clouds, so it doesn't really know.
So all the semantic is pre-processed during the calculation of the heat map. So for the policy, it's just take in the point clouds and the highlighted point cloud for each affordance. So it does not really care about semantics. So that's why, like for example, during the policy training, we can train the robots try to pick up, say, orange, and then during the executions, we try to let the robot to pick up a broccoli, which I've never seen during the training, but we can still try to pick up the broccoli, because for the policy input, it's don't really care what is a orange, what is broccoli, just a piece of point cloud with grasping of what is highlighted.
So this kind of object agnostic
Yeah.
inputs is sort of give you some generalizability.
Yeah, exactly. So we just filter out the semantics during this heat map calculation, during this intermediate representation.
So, so the diffusion output include what? Include the grasping position and the grasping pose. Does it
No.
go this
So
level?
diffusion policy just output the joint command. It's just the pure imitation learning policy.
Okay.
Yeah.
Okay. Okay. But I guess how to, given different object, how to, where to grasp and, how the pose, what pose to use to grasp. So that's all kind of implicitly encoded in the joint, the joint command you calculated from the diffusion.
Yeah. So basically, we just train the policy with, say, 2400 rollouts, right? So in this rollouts, we have some like say the middle size spherical shape object, or like the large size spherical object, small size spherical object, or middle size long objects. And then in that case, it's implicitly learn how to grasp this kind of point clouds during the demo. And then during executions, whenever you highlight another point cloud, which is roughly a spherical shape, and then it will just try to, it already know how to graph those kind of spherical shape, like how to graph those point clouds with some pre-knowledge of the from data set. Yeah, it cannot generalize to a novel shape. Yeah, it can generalize to a novel semantic, but not a shape. If you never seen, like, for example, how to grasp a screwdriver properly during a demonstration, then it will not know how to grasp it. It will probably just treat it as a snake toy. So it will just grab at the middle instead of the grab from the handle.
Okay. Yep.
All right. So this is zero shot executions. And so we just do some comparison, especially with the DP3, which is the 3 diffusion policy, which input is the 3 point clouds. But in this case, they don't filter out the semantic meaning, right? So we have to make sure the policy is executed in distribution. Otherwise, it cannot actually generalize to some new object, even with the same shape but different semantic meanings. And for the pi 0, it's really bad because it's partially because the pi 0 is not trained on this embodiment. So we have the quadruped with ARM, which has never seen during the pi 0 pre-training set. But in this case, we let the pi 0 to output the end effector pose and the body pose. So they also have some mobile manipulation demonstration in their training set, but still the pi 0 is not really good. I think we haven't, like, during this project, the Pi 5 is not come out yet, but I assume the Pi 5 will be very similar behavior to Pi because they have some fundamental limitations in these cases. So here is the few shot adaptation, which is I mentioned previously, how the robot to learn the embedding by itself. It's a supervised learning. So here, for example, we provide a text prompt. We tell the robots, okay, you're gonna sort the vegetables and place it into the basket. And then we just provide 10 human demonstrations for the robot to pick up different vegetables, and then let the robot to learn what is the meaning of what is the meaning of vegetables. So in this case, for example, at the very beginning, the heat map does not know which object you're actually grasping and where you're gonna place it. But after we do like several steps of the self-supervision learning, it will gradually know like what I gonna grasp and what I gonna place. So it's just so we just use the 10 human demo to self-supervise the heat map tuning method to convert from the text prompt to the heat map, instead of using a off-the-shelf model, for example, the Dino or the Clip, to manually specify the corresponding heat map. So here we let the policy to automatically learn the heat map classification for that affordance. So here's another example. We try to clean the table with towel and avoidant plate. So each affordance corresponding heat map is very vague at the very beginnings. But during the self-supervision learning, you can see it's gradually clear. Okay, it's try to learn what is the proper part of the point cloud should be highlighted for the affordance, for the indirect target, for the grasp. So this is the basic idea. And once we have that, the following will be the same. It just do the following execution with diffusion policy. And here we also compare with the Pi0, the DP3, and the scale. This is from Gao Yang's group from Tsinghua. And same, like the success rates are a little bit lower compared to the previous one, because previous one we used the off-the-shelf heat map assignment, so which is more accurate than the self-supervised learning. But still, like we have some notable performance gap between the baseline and our method. Yeah, I think that's pretty much all I have. Yeah, any questions? I'm happy to answer.
Okay, all right. Thanks, Yuxin. This is a very nice presentation. Let's give applause. So I have maybe still questions on the second part. So you talk about this long horizon tasks, and
Yeah.
I do see some of the tasks is more sequential. You know, you do A, then B, and then C.
Yeah.
And then the last one you showed is sort of like in parallel. You know, you need to do A and at the same time avoid collision with the plate, right?
Oh yeah. Yeah.
Do A while doing B or maybe not doing B. So
Yeah.
I'm just curious from the language instruction perspective, how how complex you can go. Can you go even more complex, in parallel language commands, or maybe even longer language sequence? Does it matter? Or it doesn't matter as long as you decompose this language instructions into sub skills, and then you can just run your diffusion policy.
Yeah, I think
Yeah.
yeah, I think we tried. I think this is the most complex task we can go. Anything beyond
Yeah.
this is too complicated, because during the diffusion policy training, we don't train this kind of tasks, right? We train more modularized
Yeah.
tasks. We just train clean the table or just avoid some object. And then during execution, we need the policy to combine two different
Okay.
modality. So
Yeah.
this is very challenging. So
Yeah,
actually, I actually doubt it can do even like more. I think the long horizon itself, like the sequential, is not hard. It's just like combining different modality at the same time in parallel is really challenging.
Yeah,
So I think in this case, it just try to combine two motion, avoiding while pick and place. So I think A plus B is what it can do at most. It cannot do A plus B plus C.
Yeah. Yep. Cool. All right. I think we can open the floor for more questions.
I did have one question from the first section of the talk.
Okay.
So if I understand correctly, the kind of like the task description that you give, you said there's kind of three different options of the contact points versus the language description versus the direct point.
Yep.
But there was one task that I saw with the basket,
The
where
basket.
where you kind of have the arm pass through it to hold the basket kind of in like the crook of the arm. And that one just jumped out to me because that seemed like a task where you need kind of more information beyond just the end effector. Like you need some kind of kinematic information about the arm. So I was just curious about like what you specify in that task. Is it just the end effector and you can kind of like pass it through the basket and kind of slide the basket back, or if there was something else going on there?
Sure. That's a very good question. So, so in the basket task, I think we only demonstrate two way, right? So the direct contact, a direct target, which is pretty much just tile operations. So you can see the reasoning is fully by the human, right? We just do the tile operations by human, and and we also demonstrate whether we can do it through. Wait, My laptop's freeze. So we also showcase how we can do it from the contact point planning. So in this case, if you check this basket video, so we specify two contact points. One is here, one is here on the 3D point cloud. So in that case, we also try to guide it through a sequence of contact points to try to actually go into the hook of that basket. And we didn't show the GPT is because the GPT right now, we can't actually let it to generate those fine-grained sequence of contact points. Because here, as you mentioned, it involves some spatial reasoning. And in that case, right now the GPT is not capable to do that. So the GPT demo, we only showed this to the yoga ball and the tool chest. So in that case, just single contact or one shot is enough. Once you have contact, you lift it up, it's fine. But those involving like spatial reasoning or a real-time feedback, for example, this task, the deck box task, this looks simple, but actually it's really challenging because we use a lag to lift up this very giant lid, and then you have to make sure the contact have to keep stabilizing this lid, and then if the contact slightly slip, so you can see there's no external handle for this lid, so you actually just have a point contact. So if the contact slip a little bit, the whole dynamics change. It's very likely the robot the lid just close it up again. So in this case, it involves some closed loop, right? You have to interact, see if the contact change, how you're gonna behave. So in that case, we can do it now. So either the real-time feedback or the spatial reasoning, in that case, we can actually handle it correctly right now.
Yeah, okay, cool. That makes sense.
Yeah.
I'm curious, are there to kind of connect the two parts of the talk, maybe you could kind of group the behavior into the direct.
That's our initial plan. So we try to say whether we can deploy this relic as the low-level controller to the Saga and to the high-level planner, but
yeah,
we don't have time. So now it's more like two separate projects. But initially we try to say, okay, if we say still the yoga ball, if say, okay, just grasp the yoga ball and the yoga ball is highlighted, and then the sequential low-level controller will use the relic, it will be a fantastic demo. So to connect the two parts together.
Yeah.
But we don't have time to do that.
Yeah, that would be cool though. I'd like to see that.
Yeah.
Cool. Thanks.
Yeah, thanks, Max. So I have one more question about the force, force information. I guess maybe related to both parts. I think it's maybe force, or contact information is not maybe incorporated in either of this work, but I can clearly see, this contact-rich manipulation problems. If you know the contact forces, or even when you use the arm elbow, joint to hold the basket, if you can estimate the payload and contact forces, that will be helpful. And for the second part, I think even when we design these diffusion models, when you grasp different objects, even the object have same geometry, same point clouds, but it's some maybe like a kind of glass bottle, maybe some is plastic bottle. So how much force you exert? I think if you incorporate the force information as the input to your diffusion, that's can be more helpful to this, contact-rich problems. I'm just curious in general, do you see there's a potential, or what is the capability of the Spot hardware can do or cannot do for force estimation?
Yeah, I think Spot right now they don't really have those force concept, but I do see I think right now many people are trying to incorporate the tactile information to the manipulations. I think
Right.
the Yunju, they have a paper, right? They attach the tactile sensor to the gripper, and then you can grasp the clear glass, like the glass bottle or something. Yeah. For the Spot, I think, as far as I know, now like for they try to incorporate the tactile sensor to the fin gripper, like
Mm-hmm.
the Aloha style gripper
Yeah, yeah, yeah.
to the robot. But I think, for example, like in this case, the whole bot, like in the relic setting, I think the force estimation can be done by the motor itself. Like
Mm-hmm.
you can see
For the current.
the motor current change.
Mm-hmm.
Have a brief estimation. We may not need to explicitly attach a tactile sensor to the robot, but
Mm-hmm.
for a more precise, say the tabletop manipulations, I do think like adding the tactile sensor is much informative. But we tried to do this kind of task before, but like especially for the Dex hand. But I do feel those, like nowadays, like the tactile sensor can just tells you whether you are in contact or not.
Mm-hmm.
The actual, say, if we have a high resolution tactile sensor, those information is kind of limited because the contact point is still sparse. We have a H1 with Inspire hand, and that has like very high resolution pressure sensor, which is 1D tactile sensors. We thought we can collect a data set by the hand interact with different objects, and then we can see the pattern of the tactile information to guess what object you're interact with. But in reality, even if it's grasping some object, a bottle or a cylindrical shape, the contact is just like a couple points. So if you check the tactile map, it's just
Yeah.
like point contact, sound is very high, and all the rest are just zero. It's very sparse.
Yeah.
So I think I just try to I brainstorm this a lot with my lab mate as well. So I think probably either we have to make the N factor soft enough to like the actual human hand to have like most contact with the object,
Yeah.
or we just treat it as a flag, say if you have contact or not. And other than that, I think the sparse contact information is not that useful for
Mm-hmm.
the different policy.
Yeah, yeah, I think that's great, some insights.
Yeah.
Yeah, I guess the hardware, so if you just think about very finer grained manipulation problem, I think this tactile sensing community, like gel sets, right? They have
Yeah, yeah,
studied a lot in very particular setup, lab setup. They can estimate, sleep, they can do object pose estimation using this, high fidelity tactile images. But I think when we scale this up to, multi-finger hands, or maybe more complex object or even larger object, for humanoid robots, not just the
yeah,
tabletop manipulation, objects, then I think well, one thing is maybe it doesn't scale up, I think just the problem might become more complex. And the other thing is the hardware is maybe not that mature. Some of this tactile map, heat map it might not be contact. It might be contact, but it's kind of barely contact. Maybe the tactile sensor resolution is not that high, so it doesn't
yeah,
give you any useful signal. Yeah.
yeah.
So yeah, okay. I think that's
But I definitely think like the contact involved manipulation is definitely a trend for
mhm.
this year or next year. Yeah,
Yeah. Yeah, I see more humanoid people start to focus on manipulation.
yeah,
It's
yeah, exactly. I mean, because if you check the Spring Festival Gala, like the low level tracking is kind of soft. So
yeah.
if we really need humanoid to do something meaningful, like instead of
Right.
just dancing on the stage, I think definitely the local manipulation is
Yeah.
the future.
Yeah, yeah, yeah. Okay, cool. I think we're already 2:15. I assume there's no more questions. If that's the case, I guess we can wrap up the seminar. And thanks, Yuxin, for giving this nice talk. And we all gonna to definitely touch with you at
Yeah,
conference or other places. Thank you.
yeah,
Yeah.
yeah. Thank you. Nice to meet you guys.
Okay. Bye.
Bye.